In this video, we're going to describe set builder notation, which is a common way to describe a set. So set builder notation is written as, in braces, an expression, colon, the rule. So in other words, it's all things of the form expression that follow a certain rule or category. It can also be written with a vertical bar instead of with a colon, and either way is fine. So as an example, we can write the set of integer multiples of 3. So that's the set ... -6, -3, 0, 3, 6, 9, etc., in set builder notation as 3n such that n is an element of the integers. So this is read out loud usually as such that. So this is read out loud as 3n such that n is an element of the integers. So all integer multiples of 3. And that's how we would write it in set builder notation. So let me give you one to try. How would you describe the even numbers using set builder notation? And secondly, how would you describe the positive even numbers using set builder notation? So I encourage you to pause and write it out quickly, and then we'll look at it together. All right, so the even numbers, we could write that as the set of integers 2n such that n is an element of the integers. So that is the set of even integers. And what about the positive even integers? Well, we could write that in different ways. One way that we could write it is as 2n such that n is an element of the integers and n is greater than 0. Another way we could write that same set is 2n such that n is an element of the natural numbers, because remember that the natural numbers n is all positive integers, whereas z is the set of all positive and negative integers as well as 0. I wanted to point out one way of writing this that isn't quite correct. So some people try to write something like n in z such that 2n for the even integers or something like that. The issue here is that we're saying, okay, n, element of the integers, things in the integers, such that 2n. I mean, one issue here is that, that here is n equal to 2n. In this case, like n would have to be 0, or, such that 2n what? We're not saying anything about what 2n is or what 2n does. We could instead write something like n in the integers such that n is equal to 2m, m in the integers, and we'd have to specify what kind of thing m is, and that would be okay, that would be correct, but notice that this is much more efficient, this is much more concise, this is sort of the typical way we would write the even integers using set builder notation. All right, so here's another problem for you to try. So what numbers are included in the following sets? So here are 3 different sets in set builder notation. For each of these, just list out the values that are in those sets. If they happen to be infinite sets, you could use ... and just give a couple representative elements so that we get the idea. So try these out, pause, and we'll talk about them in a moment. All right, our first set is the set x in z, x in the integers, such that 3x absolute value is less than 6. So we start with an element of the integers, and then we see, does it meet the rest of the criteria? So one integer x that we could plug in is the integer 0, and does it meet the criteria that 3 times x absolute value is less than 6? Yes, that would be 0, which is less than 6. So one of the elements of this set is 0. What about the value x equals 1? 3 times 1, 3, absolute value of that is less than 6. So yes, 1 is an element of this set. And what about the element 2? 2 times 3 is 6. The absolute value is 6, which is not less than 6. So 2 is not in there. So this is the largest value in that set. What about if we plug in -1? 3 times negative 1, negative 3. The absolute value of that is 3, which is less than 6, so negative 1 is in this set. And what about if we plug in negative 2 for x? Then 3 times negative 2, negative 6. The absolute value of that is positive 6, which again is not strictly less than 6. So this is the entire set. Those are the elements that are described by that set in set builder notation. How about 2x plus 1, such that x is an element of the natural numbers? So remember, boldface n is the natural numbers. Those are the counting numbers starting with 1, 1, 2, 3, 4, 5, 6, 7, etc. And so what things are in that set? 2x plus 1, such that n is in the natural numbers. So the first natural number is 1, and the value in the set would then be 2 times 1 plus 1. That is 3. What's our next natural number? Our next natural number is 2. When we plug in x equals 2, we have 2 times 2, that's 4, plus 1 is 5, and then we'll have 7, 9, etc., etc. So that is the set 2x plus 1, such that x is in the natural numbers, all the odd numbers from 3 on up. Last one, 4 to the n, such that n is in the integers. Okay, let's see. So remember the integers, positive and negative whole numbers as well as 0. So say when n equals 0, we have 4 to the 0, which is 1. So 1 is an element of this set. When n equals 1, we have 4 to the 1, which is 4. When n equals 2, we have 4 squared, which is 16. So 16 is an element of this set, ... And in the other direction, say we have n equal negative 1, then we have 4 to the negative 1. Remember that negative exponents flip the fraction, so this is 1 over 4. 1 over 4. If we had n equals negative 2, that would be 1 over 4 squared. So n equals 2, 1 over 4 squared, or 1/16, and ... so on forever. Using set builder notation, we can describe another important set, the set of rational numbers, and that's the set of numbers that can be represented as fractions of integers. So the notation for this is a boldface q. Q is the set of rational numbers, and it is a set of elements of the form m over n, such that m and n are both integers, and n, the denominator, is non-zero. So based on that definition, I'd like you to think really quickly, just to make sure you understand which of the following are elements of q, the rational numbers. So is 0 in there? Is 1/2 in there? Is 5 in there? Is square root of 2 in there? Is 2.4 in there? Is 0.1 in there? So I'd like you again to just pause and think about that quickly before moving on. All right, so which of those are elements of q? So 0 is the same thing as, say, 0 over 1. It's also 0 over 10 or 0 over negative 3 or whatever, but it's 0 over 1, where 0 is in the integers and 1 is in the integers. So that is a yes. 0 is in the rational numbers. 1/2 is clearly already written as a fraction of integers. 1 is in the integers and 2 is in the integers, so very good. So this is also a yes. 5, just like 0 over 1, 5 could be written, it could be written as 5 over 1, or it could be written as 10 over 2, or it could be written as negative 15 over negative 3, and all those are circumstances in which 5 is equivalent to m over n for some integers m and n, where n is non-zero. So again, this is yes. Square root of 2 is somewhat famously not in the rational numbers, and we'll actually prove that later in the course, that square root of 2 is irrational. It cannot be written as an integer divided by an integer. 2.4, yeah, that can be written. So we could write 2.4 as 24 over 10, or, again, just like this, there's a lot of different potential representations of 2.4 as an integer divided by an integer. So this is yes. And similarly, 0.1 can be written, we could write it as 1/10. We could write it as negative 20 over negative 200. We could write it in lots of ways. that give it as a representation of an integer divided by an integer. I now noticed I didn't have any negative examples with negative values. Note, for example, negative 0.23 is also in the rational numbers. Negative 0.23 is equal to, say, 23 over negative 100 would be one way of writing it as an integer over an integer. One last collection of sets to describe in this video are intervals. So the closed interval AB is a set. So square braces indicate that it's a closed interval, meaning that it includes the endpoints. So that can also be written in set builder notation as x in the real numbers, such that a is less than or equal to x, which is less than or equal to b. If you were graphing those points, closed interval means the endpoints are included, so those are filled in dots. The open interval AB, that is very similar, except it does not include the endpoints, so x in the real numbers, such that a is less than x, which is less than b. If you were graphing that, you would leave the endpoints open, not filled in. Similarly, we've got half-open intervals, half-open interval from a to b, or with one of them the endpoints included and one of the endpoints not included. So this would be the half-open interval where the left endpoint is not included but the right endpoint is, and vice versa. Those are our intervals. We've also got infinite intervals, meaning they've got infinity on one or both of the endpoints. So the open interval from negative infinity to positive infinity is the same thing as the real numbers, so that's the entire real number line. The open interval from a to infinity, that would not include a, but it would include everything larger than a. And the closed interval from a to infinity, again, would now include a and everything larger. Negative infinity up to b, so that's an open interval up to b. And similarly, a closed interval up to and now including b. One comment is that it's very common to confuse the following types of sets. So the set in braces 1, 2 versus the set in parentheses 1, 2 versus in square brackets 1, 2. So note that this is a set with two elements. So braces indicates just a regular set, so that's a set containing the element 1 and the element 2. If these other two expressions indicate sets, then 1, 2, as we saw before, is the open interval containing all values between 1 and 2. So the cardinality of this set, 1, 2, is infinite. And similarly, the set 1, 2 with square braces, this is just with now closed endpoints. And so the cardinality of that set is also infinite. There are infinitely many values on that interval, whereas, as we said above, the cardinality of the set 1, 2, the set containing the elements 1 and 2, is also infinity. Is not infinity, is 2. So these are very different sets from one another. One other point, note that there's unfortunately another place where we use the same notation for different things. So 1, 2 sometimes means a point, x, comma, y, and sometimes means 1, 2, a set, an open interval. Hopefully, and these will usually be clear from context which we're talking about, but note that we can't talk about, like, say, the cardinality of the point 1, 2. So if this is a point xy, that is an element. It is not a set. It does not have cardinality. So this would be element, no cardinality because it is not a set. No cardinality. So if I ask you for the cardinality of something like 1, 2 in parentheses, I'll be talking about the set, the open interval from 1 to 2, all real numbers in between 1 and 2.